Imagine you are outside at night, doing nothing unusual, just walking, thinking, maybe heading home, maybe looking up for no reason at all. Then you see a streak of light tear across the sky. At first, it feels like the kind of thing people make wishes on. A brief meteor, a passing line of brightness, something distant. But this one keeps going. It brightens instead of fading. The sky begins to look less calm, less empty, less safe. And a thought arrives faster than you want it to. What if that is not just a meteor? What if it is bigger? What if it is coming toward Earth? What if this is not a beautiful moment in the sky, but the beginning of something much larger? What would really happen? There is something unsettling about the idea of an asteroid hitting Earth. It is a quiet kind of fear, not the kind that usually sits in front of us during an ordinary day, but the kind that waits in the background of the human mind. A thought that has likely appeared in many people at one time or another. What would actually happen? The question feels large because space feels large. When people look up at the night sky, they see stillness. They see stars holding their places. They see darkness spread so evenly that it can almost feel peaceful. But space is full of motion. Earth is moving. The moon is moving. The planets are moving. And all through the solar system, pieces of ancient rock are moving too. Some are tiny. Some are large enough to be called asteroids. Some stay far away from us. Some cross paths that bring them closer to Earth's orbit. Most people, at some point, have seen the idea through movies first. A giant rock in the sky, a countdown, a bright explosion, a planet in danger. But the real story is quieter, and in some ways, even more interesting. Because an asteroid impact is not one single kind of event. It can mean many different things depending on the object involved. A small asteroid and a large asteroid do not create the same result. A rocky one and a metallic one do not behave in exactly the same way. A shallow angle and a steep angle can lead to very different outcomes. An impact over land and an impact over the ocean can change the story again. So the question is simple, but the answer branches outward. What would really happen if an asteroid hit Earth? To begin answering that, it helps to step back and look at Earth the way space does. Our planet feels enormous to us. It carries oceans, forests, cities, deserts, clouds, and billions of lives. From the ground, it feels stable. It feels established. It feels like the fixed center of our experience. But from farther away, Earth is a small moving world, traveling through a much larger system. It circles the sun at great speed. It spins through day and night without pause. It moves through a region of space that contains dust, fragments, ice, and rock left over from the early solar system. Much of that material never comes near us in any dangerous way. Some of it burns up harmlessly high in the atmosphere as brief streaks of light. That is what a meteor usually is. A tiny visitor ending in a flash. But the solar system also contains larger bodies. Objects old enough to come from the earliest chapters of planetary formation. Fragments from a time when worlds were still taking shape. Pieces that never joined a planet, and instead remained in orbit around the sun for billions of years. That is part of what makes this subject so striking. An asteroid is not just a random rock. It can be a remnant from the beginning. A survivor from an age before Earth looked the way it does now, before trees, before birds. before people stood beneath the sky and asked questions about what might be out there. And sometimes one of those objects crosses Earth's path. That does not mean disaster is always near. Large impacts are rare on human timescales. Earth is hit by tiny material all the time, and almost all of it causes no real harm. The atmosphere protects us constantly. It acts like a shield against countless small arrivals. Still, the larger objects hold our attention for a reason. They remind us that Earth is part of a bigger cosmic setting. They remind us that our world is beautiful, living, and sheltered, yet still moving through open space. They remind us that the sky above us is not empty. It is active. It is historical. It is filled with objects following paths that began long before human civilization. So when we ask, what would happen if an asteroid hit Earth? We are really asking several questions at once. What kind of asteroid? How large? How fast? From what angle? And where? Each of those details changes the answer. Some impacts would never reach the ground. Some would burst in the atmosphere. Some would strike with local force. And some, if large enough, could alter the course of life on a planetary scale. That is where this story begins, with one world beneath a moving sky, and with one question that has followed humanity for a very long time. Before we can understand what happens when an asteroid hits Earth, it helps to slow down and look at the object itself. Because the word asteroid can sound bigger, stranger, or more dramatic than it really is. And yet, at the same time, it can also hide just how important these objects are. An asteroid is, in the simplest sense, a rocky body traveling through space. That is the basic idea. Not a star, not a planet, not a comet with a long, bright tail. Just a solid object, usually made of rock, metal, or a mixture of both, moving around the sun. But even that simple description leaves out the deeper part of the story. Asteroids are old, extremely old. Most of them are leftovers from the early solar system, formed more than 4.5 billion years ago, when the sun and planets were still taking shape. Back then, the solar system was not the orderly place we imagine now, with planets calmly following familiar paths. It was crowded, violent, and unfinished. Dust and gas swirled around the young sun. Tiny grains collided and stuck together. Those grains became pebbles. Pebbles became larger clumps. Larger clumps became planetesimals, which were early building blocks of planets. Some of those building blocks kept growing. Over immense stretches of time, they became worlds. Others never made it that far. They were broken apart, scattered, pulled by gravity, crushed in collisions, or simply left behind. Many of those leftovers are what we now call asteroids. So when we look at an asteroid, we are not just looking at a random rock drifting in darkness. We are looking at a surviving fragment from the solar system's beginning, a piece of deep time, a remnant from an age before Earth had oceans, forests, or life. That alone makes asteroids interesting. They are not modern objects. They are ancient ones. Most asteroids are found in the asteroid belt, a broad region between Mars and Jupiter. This does not mean they are packed tightly together, like stones in a pile. The belt is actually very spread out. A spacecraft can pass through it without weaving between endless rocks. But over that large region, there are many asteroid bodies orbiting the Sun. Why did a planet never form there? A big part of the reason is Jupiter. Jupiter's gravity is enormous. Its influence helped stir that region so strongly that much of the material there had trouble settling into a single planet. Instead of quietly building one world, many objects remained separate. They collided, broke apart, and continued circling the Sun as smaller bodies. That is why the asteroid belt is not a failed solid ring. It is more like a broad zone of ancient leftovers shaped by gravity and time. Asteroids themselves come in many forms. Some are made mostly of rock. Some contain large amounts of metal, especially iron and nickel. Others are darker and richer in carbon-based material. These differences matter because composition affects how an asteroid reflects light, how dense it is, and how it might behave if it entered Earth's atmosphere. A loose, fractured asteroid is not the same as a dense metallic one. Even if two asteroids are roughly the same size, they may not deliver the same outcome. This is part of why scientists care so much about what an asteroid is made of, not just how big it is. Shape matters too. When people picture an asteroid, they often imagine a nearly perfect round stone. But many asteroids are irregular, lumpy, misshapen. Some look more like broken mountain fragments than smooth worlds. They have been shaped by impacts, fractures, and gravitational limits over immense spans of time. The larger objects in the solar system tend to become round because their own gravity pulls them inward from all directions. But many asteroids are too small for that. Their gravity is weak, so they keep their uneven shapes. Some are even thought to be rubble piles. That means they may not be one single solid block at all. Instead, they can be collections of broken pieces held together loosely by gravity. In a sense, some asteroids are less like one giant stone and more like a drifting cluster of wreckage. This matters a great deal. A rubble pile asteroid may break apart differently than a more solid one. It may respond differently to heat, pressure, or a deflection attempt. Again, the word asteroid sounds like one category, but in reality, it includes many different kinds of bodies. There is also an important difference between asteroids and meteoroids. A meteoroid is usually smaller, much smaller. If a little piece of rock enters Earth's atmosphere and burns up, we usually see it as a meteor, which is the streak of light often called a shooting star. If part of that object survives and reaches the ground, it becomes a meteorite. Asteroid is generally the word used for the larger parent body in space, so the language changes depending on size and stage. Rock in space, light in the sky, fragment on the ground. This helps us separate the ordinary from the extraordinary. Earth is constantly encountering tiny material from space. That is normal. That is part of living on a planet with an atmosphere. The larger objects are rarer, but they are the ones that shape our imagination. Because a truly large asteroid is not just another speck burning up above us. It is a world fragment crossing paths with a living planet. And that is why understanding what an asteroid is matters so much. It is a leftover from formation, a witness to the earliest solar system, a body shaped by collisions, gravity, and time. Sometimes rocky, sometimes metallic, sometimes solid, sometimes more like a loose heap of debris, always ancient. And if one ever comes toward Earth, all of those details begin to matter. Because from far away, an asteroid may look like only a small dark object against space. But in reality, it carries history, structure, motion, and force. And the next question is the one that changes everything. How big is it really? When people imagine an asteroid hitting Earth, they often imagine one version of the event. One enormous rock. One global disaster. One moment that changes everything. But in reality, asteroid impacts do not belong to one single category. They exist on a scale. And that scale matters more than almost anything else. Because size changes the story. A very small object from space may never reach the ground at all. A somewhat larger one might survive part of its descent and explode in the atmosphere. A larger one still could damage a city or a region. And at the highest end, a truly massive asteroid could affect the entire planet. So when we ask what would happen if an asteroid hit Earth, the first real question is not just whether it hits. It is how big it is. That one detail shapes nearly everything that follows. If the incoming object is tiny, Earth may barely notice it. Small fragments from space enter our atmosphere all the time. Many are no larger than grains, pebbles, or small stones. They strike the atmosphere at high speed, heat up rapidly, and burn away long before they can reach the ground. What we see from below is often just a streak of light, brief, beautiful, gone in a second or two. That kind of event is common. It is part of the normal relationship between Earth and space. But as the object becomes larger, the atmosphere has a harder time stopping it. A space rock several meters across is no longer dealing with the atmosphere in the same way as a tiny grain. Now there is more mass, more momentum, more energy to release. Some of these objects still do not reach the surface intact. Instead, they break apart violently in the sky. This can create what is called an airburst. The asteroid or meteoroid tears itself apart under pressure and heat before impact, releasing a burst of energy high above the ground. That might sound less dangerous than a direct strike, but it can still be extremely destructive. The shock wave from an airburst can race outward with enough force to shatter windows, damage buildings, and injure people far below. So even when the ground is never touched, the event can still feel like an explosion from the sky. Then there are larger objects, the ones that can survive much more of their descent. At this scale, a direct impact becomes more likely. And once that happens, the event changes completely. A ground impact is not like dropping a rock into dirt. It is not even close. At cosmic speeds, the incoming object carries extraordinary kinetic energy. When it strikes, that energy is released in a violent instant. Rock, soil, and metal compress with such force that they behave in ways far outside everyday experience. Material can melt, vaporize, blast outward. The surface itself becomes part of the explosion. And still, even here, size continues to divide one kind of disaster from another. A smaller impactor might create a local event, severe destruction near the strike zone, damage spreading outward, but mainly concentrated in one area. A larger one could devastate a whole region. A larger one again could alter weather, darken the sky, and disturb ecosystems far from the crater itself. And at the extreme end are the rare giant impacts that do not simply damage part of Earth, but change the conditions of life across the planet. This is why asteroid discussions can be misleading when size is left vague. People may hear the word asteroid and imagine one standard threat. But an object 20 meters wide is not the same as one 200 meters wide. And one 200 meters wide is not the same as one 10 kilometers wide. those are not just bigger versions of the same event. They are different categories of consequence. The difference is not linear. It grows quickly. A modest increase in size can mean a very large increase in mass. And because impact energy depends so strongly on mass and speed, the consequences can rise dramatically. That is why scientists pay such close attention not only to whether an object might approach Earth, but to how large it is estimated to be. The diameter helps reveal the range of possible outcomes. There is also another reason size matters. It affects what Earth's atmosphere can do. Our atmosphere is a remarkable shield, but it is not equally effective against everything. It handles tiny objects very well. It can weaken or destroy some larger ones. But beyond a certain size, the atmosphere becomes less of a barrier and more of the first stage of impact. So the incoming object's size determines not just how much damage it might cause, but where the story unfolds. High in the atmosphere, lower in the sky, or at the ground itself. And that means the phrase asteroid impact hides a wide range of realities. Sometimes it means a harmless flash. Sometimes it means broken glass and a shockwave. Sometimes it means a crater. Sometimes it means something far worse. So before we can understand what an asteroid hit would really look like, we have to hold on to one simple truth. Not all space rocks arrive the same way. Not all of them survive the same way. And not all of them change Earth by the same amount. Some pass like sparks, some arrive like explosions, and some are large enough to leave marks on the history of a planet. A natural question follows once we understand size. Why does an asteroid hit so hard in the first place? After all, an asteroid is just rock, or metal, or some mixture of both. And on Earth, a rock is not usually the most frightening object we can imagine. But in space, motion changes everything. Because an asteroid is not simply falling, it is traveling. And it is traveling very fast. This is one of the most important parts of the whole story. An asteroid does not drift gently toward Earth like a leaf falling through air. It moves through the solar system at enormous speed, already carrying energy long before it ever comes near our planet. That speed comes from orbit. Asteroids move around the Sun just as planets do. Earth is also moving around the Sun. So when an asteroid approaches Earth, this is not a case of one still object waiting for another. It is a meeting between bodies already in motion. Earth is racing along its orbital path. The asteroid is following its own path. Sometimes those motions partly align. Sometimes they meet more directly. The exact geometry can differ, but the result is the same. The closing speed can become immense. This is why asteroid impacts are so violent. The danger is not just what the asteroid is made of. It is how much kinetic energy it carries. Kinetic energy is the energy of motion. The faster something moves, the more of it has. And when speed rises to extreme levels, the energy rises very quickly. That is why a small object moving slowly and a small object moving incredibly fast are not remotely the same thing. Speed turns mass into force. This is difficult to picture using everyday life, because almost nothing in ordinary experience moves at asteroid speed. A thrown rock is slow. A speeding car is slow compared with an incoming asteroid. Even a bullet, fast as it feels to us, exists in a very different range of motion than many objects arriving from space. An asteroid can enter Earth's atmosphere traveling at many kilometers per second. Not per hour, per second. That means in the time it takes to blink, it may have crossed distances that would feel enormous on the ground. And that is why impact is such a misleading word if we imagine it too gently. Impact sounds like contact, a strike, a collision. But at these speeds, it is closer to a sudden release of tremendous stored motion. When the asteroid meets Earth, that energy has to go somewhere. It does not simply stop. Instead, the energy is transferred into the ground, the atmosphere, and the asteroid itself. Rock is crushed. Heat rises rapidly. Shock waves spread outward. Material can melt or vaporize. The event becomes explosive, even though no chemical bomb is involved. The explosion comes from motion being converted into heat, pressure, and destruction in an instant. This is the part that makes asteroid impacts different from many disasters people are used to imagining. The asteroid does not need to be on fire in space to be dangerous. It does not need to explode like a movie weapon. Its power is already present in its speed, and Earth's gravity adds to that final descent. As the object approaches, Earth pulls on it. Gravity can increase its speed further as it falls inward. So the asteroid arrives not only with the momentum it already had from orbit, but with extra acceleration during the last stage of its approach. The result is a collision shaped by both solar motion and planetary gravity. This also helps explain why even a modest-sized asteroid can create an event far beyond what its size might suggest. A person might imagine a rock the size of a house and think of something heavy, but limited. Still dangerous, but not extraordinary. But if that object is moving at cosmic speed, the outcome is no longer comparable to a house-sized rock falling from a cliff. The scale of released energy becomes far greater, and this is why scientists pay attention not only to diameter, but also to velocity. Two asteroids of similar size may not produce the same result if one is moving much faster than the other. Size matters greatly. Composition matters too. But speed is one of the great multipliers. It determines how violently the object meets the atmosphere, how much energy is available at impact, how severe the shock wave may become, and how much of Earth's surface and sky are drawn into the event. So when people ask what would happen if an asteroid hit Earth, part of the answer begins here. It would hit with force because space is not still, because the solar system is full of bodies already in motion, because Earth itself is moving through that motion every second, and because when those paths intersect, even a simple rock can arrive carrying extraordinary energy. That is the hidden power of asteroid impacts. Not just mass, not just size, speed. And before any crater forms, before any dust reaches the sky, before any shock wave spreads across the ground, the asteroid must first meet something else: air. Before an asteroid reaches the ground, it reaches something else first: air. That may sound simple, but it matters more than it seems. Because Earth does not sit naked in space. It is wrapped in an atmosphere, a deep envelope of gas surrounding the planet. And that atmosphere changes the story of incoming objects immediately. This is the first barrier an asteroid meets. For very small objects, it is often enough. Tiny pieces of rock enter Earth's atmosphere all the time. Most never come close to reaching the surface. They strike the upper atmosphere at tremendous speed, and almost at once the encounter begins to turn violent. Not because the object is rubbing against the air in the ordinary sense people may imagine, but because the air in front of it is being compressed extremely fast. That compression matters. When air is crushed suddenly, its temperature rises. So as the incoming object plows into the atmosphere, the gas ahead of it heats up intensely. The object is surrounded by a growing envelope of extreme heat. Its outer layers begin to glow. Material starts to burn away, melt, or flake off. From the ground, this may look beautiful. A bright streak in the sky, a sudden line of white, yellow, or orange light. Something brief enough to feel almost peaceful. But what we are really seeing is a fast object undergoing stress, heat, and erosion as it tears through Earth's protective shell. This process is called ablation. Ablation is the wearing away of material from the object's surface as it encounters the atmosphere at high speed. Bit by bit, the outside is stripped away. The smaller the object, the more completely this can destroy it. This is why so many space rocks never become impact events at all. The atmosphere handles them first. In a way, the sky catches them. But this protection has limits. As the incoming object becomes larger, the atmosphere has a harder time stopping it. A bigger asteroid has more mass, more momentum, more stored energy. It can keep pushing downward even while its surface is burning away. And size is not the only factor. Composition matters too. A loose, fragile object may break apart more easily. A denser metallic object may survive longer. An asteroid made of stronger material can endure stresses that would destroy a weaker one. So two objects of similar size may behave very differently once they enter the atmosphere. The angle of entry also changes the story. If the object comes in at a shallow angle, it may spend more time moving through the atmosphere. That gives the atmosphere more opportunity to slow it, heat it, and tear it apart. If it comes in at a steeper angle, it may plunge downward faster, passing through more directly toward the ground. So even before impact, several details are already shaping the outcome. Size, speed, composition, angle. All of them begin to matter the moment the object reaches air. And the atmosphere does more than heat the object. It also pushes against it. As the asteroid dives deeper, pressure builds across its surface. If the stress becomes too great, the object can fracture. Cracks can spread through it. It can begin to break into pieces. Each fragment then creates its own path of heat and pressure. Sometimes that breakup is gradual. Sometimes it is sudden and violent. This is one of the key reasons the first atmospheric contact is so important. It determines whether the object stays intact, weakens, explodes in the sky, or survives far enough to strike the surface. In some cases, the atmosphere turns a possible crater into nothing more than a flash. In other cases, it turns one incoming object into many falling fragments. And in larger cases, it becomes only the opening stage of a much bigger event. That is why Earth's atmosphere is both shield and threshold. It protects us from countless small objects every day. Without it, the planet's surface would be struck far more often by material from space. The quiet safety people feel beneath the sky depends in part on this invisible layer of gas above them. But for larger incoming bodies, the atmosphere does not always stop the event. Sometimes it only transforms it. It turns darkness into a streak of light. It turns motion into heat. It turns stone into plasma, fragments, and fire across the sky. And if the object is large enough, the atmosphere is not the end of the story. It is only the beginning, because some asteroids never reach the ground. Yet they still explode with enough force to cause real damage below. And that means the next kind of impact does not happen on Earth's surface at all. It happens in the sky. Not every dangerous asteroid event ends with a crater. Some never reach the ground at all. That may sound less severe at first. If the object does not strike the surface, it can seem like the danger has somehow been avoided. But that is not always true, because sometimes the atmosphere does not stop the event quietly. Sometimes it turns it into an explosion in the sky. This is called an airburst. An airburst happens when an incoming object breaks apart violently in the atmosphere before it can reach the ground. By this stage, the object is already under enormous stress. It is moving at tremendous speed. The air in front of it is heating intensely. Pressure is building across its surface. Cracks may already be spreading through it. Then, at some point, the object can no longer hold itself together. It fractures, breaks apart, and releases a large amount of energy high above the surface. This is important to understand. An airburst is not just a rock crumbling quietly in the sky. It is a sudden atmospheric explosion caused by extreme speed, pressure, and breakup. The energy that would have remained concentrated in one falling body is instead released rapidly through the air, and the air carries that force outward. One of the most dangerous parts of an airburst is the shock wave. When the explosion happens, a powerful pressure wave can spread downward and outward through the atmosphere. That wave can reach the ground with enough force to shatter windows, damage buildings, knock people down, and cause injuries across a large area. Even without a crater, the event can still become a serious disaster. So an airburst belongs in its own category. It is not the same as a harmless meteor burning up. And it is not the same as a direct ground impact. It is something in between, where the atmosphere itself becomes the main stage of destruction. One of the clearest modern examples happened in 2013 over Chelyabinsk, Russia. A relatively small asteroid entered Earth's atmosphere and exploded in the sky. It never created a major ground crater like people often imagine in asteroid movies. But the event still caused widespread damage. The flash was extremely bright. The shock wave shattered windows across the city. Many people were injured, largely by flying glass after they moved toward windows to look outside. That event mattered for a reason. It reminded the world that even a modest asteroid can become dangerous before ground impact ever happens. The sky itself can deliver the force. And it also showed how strange the timing of such an event can feel to people on the ground. First comes the light. A bright flash may appear in the sky, sometimes more brilliant than expected, sharp enough to draw immediate attention. People look up, they pause. They try to understand what they are seeing. Then, because light travels faster than sound and pressure waves, there can be a delay. For a few moments, everything may seem strangely quiet again. And then the shockwave arrives. Windows burst inward, buildings shake, car alarms sound. People are thrown into confusion. The event unfolds in stages, which can make it even more disorienting for anyone underneath it. Falling fragments can also create danger. When the main body breaks apart, smaller pieces may survive and continue downward. Some may burn away further, some may land as meteorites. Most fragments are much less destructive than the main atmospheric blast, but they can still injure people or damage property if they reach the ground. So an airburst can harm through several different paths. There is the flash, there is the shock wave, there is shattered glass and structural damage, and there may also be falling debris. That is why a ground impact is only one kind of asteroid disaster. An airburst is another. In some cases, it may even be the more likely outcome for certain incoming objects, especially those that are large enough to survive deep into the atmosphere, but not strong enough to stay intact all the way to the surface. This makes the atmosphere feel different now. In the last section, it seemed like a shield, and it is. It destroys countless small objects and protects Earth constantly. But here we see another side of it. For some incoming bodies, the atmosphere does not simply stop the threat. It concentrates it, transforms it, and sends it outward across the sky as a sudden blast of heat, light, and pressure. So even when an asteroid never touches the ground, Earth can still feel the event deeply. And when an object is large enough or strong enough to survive past that stage, the story changes again. Because then the explosion in the sky gives way to something even more violent: the surface itself. If an asteroid survives its descent through the atmosphere and reaches the surface, the event becomes brutally fast. There is no slow build-up at that point. No gradual settling. No ordinary collision. The moment the asteroid meets the ground, an extraordinary amount of energy is released in an instant. This is important to picture correctly. A ground impact is not like a large rock falling onto Earth, the way a boulder might fall down a mountainside. It is not even like a powerful explosion in the everyday sense. It is a collision at such extreme speed that both the asteroid and the ground are forced into conditions far beyond ordinary experience. For a fraction of a second, the asteroid and the surface compress violently against one another. The energy of motion, which the asteroid carried across space, suddenly has nowhere left to go. It is dumped into the impact site all at once. That compression creates enormous pressure. At such pressure, familiar materials stop behaving in familiar ways. Solid rock no longer responds the way we think of rock responding. It does not simply crack like a sidewalk stone or break into a few rough pieces. Under impact conditions, rock can behave more like a fluid. That sounds strange, but it helps explain why craters form the way they do. The pressure is so intense that the surface briefly flows, surges, and blasts outward. The asteroid itself is also being crushed, broken, melted, and in many cases, partly vaporized. So the event is not just a hard object striking a hard surface. It is more like two masses of matter forcing each other into a violent state of shock. Heat rises rapidly. The temperatures at the impact site can become extraordinary, high enough to melt or vaporize material in and around the point of contact. This is one of the reasons an asteroid impact is so destructive, even before we start thinking about the larger crater or the wider blast zone. The impact site becomes a place of sudden transformation. Solid ground becomes shattered and displaced. Rock may melt. Material may be thrown upward and outward. A flash of heat and light can accompany the strike. The surface is no longer stable terrain. It becomes part of the impact itself. And all of this begins almost instantly. That is one of the hardest parts of asteroid impacts to grasp. The scale may be huge, but the opening moment is incredibly short. The initial contact, compression, and shock happen in far less time than human reactions can keep up with. By the time anyone near the impact site could process what is happening, the most violent first stage would already be underway. A crater begins forming almost at once, not because the asteroid slowly digs into the ground like a shovel, but because the force of the collision blasts material away from the point of impact. The asteroid's energy drives into the surface and sends shockwaves through both the ground and the object itself. Those shockwaves help excavate the crater, pushing rock and debris outward in every direction. So the crater is not simply a dent. It is the visible result of an explosive release of motion, pressure, and heat. Much of the asteroid's energy spreads outward from that first instant. Some of it becomes heat. Some becomes shock, traveling through the ground. Some becomes a blast wave moving through the air. Some becomes flying debris, with shattered rock and ejecta thrown high and far from the strike zone. And some goes into reshaping the surface itself, beginning the excavation of the crater that will define the impact site. This is why the first moment of ground impact contains so much of the event's power. It is the turning point where motion becomes destruction. Before impact, the asteroid is still an object in transit. It is a body crossing space, descending through air, carrying ancient history and immense speed. At impact, that long journey ends in a fraction of a second, and the force that had been contained in its motion is released into Earth. That is the true power of the moment. Not just that something hits the planet, but that speed, mass, and pressure all meet at once, forcing rock, metal, and ground into an instant of chaos that no ordinary collision can resemble. And from that instant, the next stage begins. Because once the first contact is over, the crater does not simply appear all at once. It grows through a sequence of intense stages. Contact, excavation, then settling. In other words, a crater is not just a hole left behind. It is an explosion written into the ground. A crater may look simple once it is finished. A round hole in the ground, a scar left behind, a place where something struck long ago. But the way a crater forms is anything but simple. It is fast, intense, layered, and far more dynamic than the final shape suggests. A crater is not made in one neat motion. It forms through stages. The first stage is contact and compression. This is the instant we just arrived at in the last section. The asteroid reaches the surface, and its enormous kinetic energy is released into the ground. For a moment, both the asteroid and the surface are compressed under extraordinary pressure. Shock waves move outward through the asteroid and downward into Earth. Temperatures rise sharply. Material begins to melt, fracture, and in some cases vaporize. This stage is extremely brief. It is the opening blow, the first instant in which motion is converted into pressure, heat, and destruction. But it does not last long, because the energy released here immediately drives the second stage. That second stage is excavation. This is where the crater really begins to open. The shock waves and released energy blast material outward from the impact point. Rock and soil are thrown up, out, and away. The ground does not simply sink under the asteroid. It is excavated in an explosive burst. This is why a crater is not best imagined as a punched hole. It is closer to a blast cavity. Material is forced outward in every direction. Fragments of rock, dust, and molten debris can be launched high into the air. Some falls back close to the crater. Some can travel much farther. The ground around the impact site becomes part of the event, lifted and thrown outward by the force of the strike. During this stage, what scientists sometimes call the transient crater forms. This is the temporary cavity created during the most explosive part of excavation. It is not always the final shape that remains. It is more like an unstable first version of the crater, formed while the energy is still pushing material outward. Then comes the third stage, modification. This is the stage where the crater begins settling into the shape that will remain after the most powerful motion has passed. The walls may slump inward. Loose material may slide downward. The floor of the crater may shift and rebound. The final structure starts to emerge. This matters because the crater people see later is not always identical to the first cavity, blasted open during excavation. The impact creates the initial opening, but gravity and collapsing material help shape what remains. In smaller impacts, the final crater may look like a simple bowl, a rounded depression with raised edges, fairly straightforward in form. But larger impacts can produce more complex shapes. When the impact is powerful enough, the crater floor can rebound upward after being driven down by extreme force. This rebound may create a central peak, a raised structure near the middle of the crater. The walls may also collapse in stepped patterns, creating terraced edges. So the final crater is not always a plain hole. It can be a large, complex landform with inner slopes, uplifted centers, and layers of collapsed material. This is another reason asteroid impacts are so unusual. The final crater can be far larger than the asteroid itself. That may seem surprising at first. We might expect the hole to match the size of the incoming object. But because the impact is driven by energy, not just physical contact, the surface response can extend well beyond the asteroid's own width. A relatively small object, moving at extraordinary speed, can produce a crater many times larger than itself. The ground is not just being touched by the asteroid. It is being shocked, excavated, and thrown outward by an explosive release of motion. So the crater becomes a kind of record, a physical memory of the energy that arrived there. It tells us that something from space struck with enough speed and force to crush, melt, excavate, and reshape the surface in seconds. It is not just a mark of contact. It is the visible signature of a powerful transformation. And yet, even the crater is not the whole story. Because while the cavity is forming, danger is also spreading outward beyond it. Shock waves are racing through the air. Heat is moving away from the impact zone. Debris is falling back through the sky. Fire may begin across the surrounding landscape. The crater is the center of the event, but not its limit. What happens nearest the strike is only the beginning. Because once a crater is born, the world around it begins changing in seconds too. Once the asteroid strikes the ground and the crater begins to open, the surrounding area changes almost immediately. The impact site is the center of the event. But the danger does not stay neatly inside the crater. It spreads outward. This is the part of the story where the strike becomes more than a point of contact. The asteroid may hit one location, but the energy released there begins moving across the landscape in several forms at once. One of the first is the shock wave. A powerful pressure wave pushes outward through the air from the impact site. Close to the strike, that wave can be devastating. Buildings may collapse or be torn apart. Trees can be snapped, stripped, or flattened. Anything exposed near the center of the blast would face extreme force in a very short amount of time. The important thing to understand is that the damage near the crater would not come from only one cause. It would come from several at once. The pressure wave moves through the air. The ground itself can shake from the impact, adding another layer of destruction. And the heat released near the strike can create additional danger across the surrounding area. That heat matters a great deal. Near the impact zone, temperatures can rise enough to ignite fires. Flammable materials may catch quickly. Vegetation, buildings, and anything else able to burn could begin igniting across a wide area depending on the size of the impact. So even after the first blast wave passes, the landscape may continue changing as fire spreads outward from the strike region. Then there is the falling debris. When the asteroid hits, large amounts of rock, dust, and broken material are thrown up and away from the crater. Some of that ejecta rises high before falling back down. Some lands close to the crater. Some can travel much farther than people might expect. This means the sky around the impact zone would not simply clear after the strike. In many cases, material would still be coming down. Fragments of rock could rain back over the surrounding region. Dust could begin filling the air. Larger chunks of debris could strike the ground far beyond the crater edge. The impact is not just one downward event. It also becomes an outward and upward one. For anyone near the strike zone, this would create an environment that changes second by second. First the flash, then pressure, then shaking, then heat, then falling debris. And all of it unfolding so quickly that there would be little time to process any one part before the next arrived. This is why the area closest to the impact would experience the most severe destruction. Distance matters enormously. Near the crater, the pressure is strongest. The heat is most intense. The falling debris is heaviest. The ground disruption is greatest. As you move farther away, those effects begin to weaken, but near the center, they overlap in the most damaging way. That does not mean every impact creates the same surrounding blast zone. Again, size changes everything. A smaller impact may produce severe local damage. A larger one may affect a much broader region. The exact pattern also depends on impact angle, speed, terrain, and what the asteroid is made of. But in general, the closer one is to the strike, the more intense the conditions become. And this helps correct a common image people may carry from movies. An asteroid impact is not only about the crater itself. The crater is important, but it is only the center. The real event includes the blast moving outward from that center, reshaping the air, the ground, and the sky around it. So the immediate area around the strike would not feel like standing near a hole in the ground. It would feel like being near the source of a massive release of energy. Structures may be damaged or swept away. The landscape may burn. Dust and debris may darken the air. The ground may still be trembling. And the crater, newly formed, would sit at the middle of it all, like the mark left by something arriving from far beyond Earth. But even this is still only the nearest zone of damage. Because farther from the impact, the event begins to change form. The destruction is no longer centered on total ruin at the crater's edge. Instead, it becomes something people might experience in stages. A bright flash in the distance, a delay, a pressure wave arriving later, windows shattering far away, the ground trembling underfoot. In other words, once we leave the immediate blast zone, distance starts rewriting the experience of the strike. Farther from the crater, the impact would still be dangerous, but it would feel different. This is where distance begins to change the experience of the event. Near the impact site, destruction happens almost all at once. Closer to the center, the pressure, heat, shaking, and debris overlap in a concentrated way. But farther away, people would experience the strike more in stages. The first thing many people might notice is light. A bright flash could appear on the horizon or across the sky, depending on distance, terrain, and weather. It might look sudden and unnatural, far brighter than anything expected from an ordinary night. For some people, it could be the first sign that something enormous had happened. For others, it might be confusing at first, more like a strange burst of brightness than an immediately understood disaster. Then there could be a delay. That delay matters. Light reaches people much faster than sound or pressure waves do. So someone far from the crater might see the flash first, then experience a strange pause before anything else arrives. For a few moments, there may be uncertainty. What was that? Lightning, a distant explosion, something in the sky. Then the pressure wave could arrive. Depending on the size of the impact and the distance involved, that wave might come seconds later or much later. It could rattle buildings, shake walls, and shatter windows over a very wide area. Even people far from the strike zone might still feel the force of the event passing through the air around them. This is one of the strangest parts of a large impact at a distance. The source may be far away, but the event can still reach you physically. Glass breaking may be one of the most immediate dangers in these outer areas. People near windows could be injured by shards blown inward. Buildings not destroyed outright near the crater could still suffer damage far beyond it. Doors may slam, roofs may creak or shift. Objects inside homes may fall, cars may shake. Alarms may begin sounding across neighborhoods that never saw the strike itself. The ground could also move. A large asteroid impact can send seismic energy through Earth, producing shaking that feels similar to an earthquake. To people at a distance, that may be part of what makes the event so disorienting. It is not only in the sky, it is in the ground too. So the impact would not feel distant in the way people usually imagine distant things. It would announce itself through multiple layers of sensation. A flash, a pause, a wave through the air, a tremor underfoot, and then the atmosphere itself may begin to change. Dust and smoke from the impact region could spread outward and upward. Depending on the size of the event, parts of the sky may begin to look dimmer, dirtier, or strangely colored. The air may take on a hazy appearance. Sunlight could weaken. In some cases, the horizon may hold a dark rising column or a broadening cloud reaching far above the strike area. That means even people well outside the main destruction zone might begin to feel that something larger was unfolding. Not just a distant explosion, but a change in the sky itself. The farther from the crater a person is, the more the impact becomes a layered experience instead of a single overwhelming one. That does not make it safe, it just makes it different. Close to the strike, survival may be unlikely. Farther out, people may survive the main event, but still face injuries, shattered infrastructure, fire, confusion, and worsening environmental conditions. Communication systems may fail. Roads may be blocked. Emergency services may be overwhelmed. What feels at first like a distant blast may slowly reveal itself as a regional crisis. And all of this still depends heavily on size. A smaller impact might create a zone of shattered windows and local confusion. A larger one could affect cities far beyond the crater. A much larger one could begin changing the atmosphere on a scale that extends beyond any one region. So distance does not erase danger, it reshapes it. The impact becomes less about being at the center of destruction and more about watching the consequences arrive in pieces. A bright flash that makes no sense at first. a pressure wave that reaches you later, ground movement that seems to come from nowhere, dust spreading through the sky, and from there, another question begins. Because if the asteroid strikes land, the story unfolds one way. But if it strikes the ocean, where most of Earth's surface lies, the shape of the disaster changes again. Most of Earth is not land. It is water. That matters because if an asteroid were large enough to survive the atmosphere and reach the surface, there is a good chance it would not strike a continent at all. It would strike the ocean. And that changes the shape of the disaster. The basic physics are still the same. The asteroid is still arriving at tremendous speed. It is still carrying immense kinetic energy. And that energy still has to go somewhere when the object meets Earth. But water responds differently than rock and soil. Instead of excavating dry ground, the impact forces its way into the ocean, driving water outward and downward at the same time. A huge volume of water can be displaced in a very short moment. That displacement is one of the main reasons ocean impacts are so dangerous. The sea does not simply swallow the asteroid quietly. It is thrown upward, outward, and then gravity begins pulling it back into motion again. This can produce powerful waves moving away from the impact region. People often imagine a single giant wall of water racing across the entire ocean in the same form from beginning to end. The reality is more complex than that. The size and behavior of the waves depend on several factors, including the size of the asteroid, the angle of impact, the speed of arrival, and the depth of the water where the strike happens. A deep ocean impact may behave differently than a strike in shallower coastal water. A steeper impact may push energy into the sea differently than a more angled one. So once again, the event does not come in one standard version. But in general, nearby coastlines would face the greatest danger. Regions close to the strike could experience major water displacement and destructive incoming waves. Low-lying shorelines would be especially vulnerable. Ports, coastal towns, and island communities near the impact area could face severe flooding and damage. Distance matters here too. Just as with a land impact, the effects are strongest nearest the event. The farther the energy travels, the more the exact wave behavior depends on ocean conditions, seafloor shape, coastline geometry, and how the water continues redistributing that force. So an ocean impact is not simply a land impact translated into water. It becomes a different kind of spreading hazard. There is also the question of what happens above the surface. An asteroid striking the ocean does not only affect the sea, it can also affect the atmosphere. The impact may blast water vapor high upward along with mist, debris, and aerosols. If the asteroid is large enough, the event could inject enormous amounts of material into the air. Saltwater spray, fine particles, and vaporized matter may all become part of the aftermath. That means an ocean impact can still influence the sky, not just the water. So even though it may not produce the same kind of crater-centered landscape destruction as a land strike, it can still create a broad regional disaster and, in larger cases, contribute to wider atmospheric effects. This is part of what makes asteroid impacts difficult to reduce to one image. If it hits land, people picture a crater, a blast wave, falling debris, and fire across the surrounding area. If it hits the ocean, the energy moves differently. The sea becomes part of the event, carrying danger outward through water as well as air. And because the oceans cover so much of Earth, this is not a side scenario. It is one of the main possibilities. That makes the ocean feel different too. Usually, it can seem like open water would be the safer place for such an impact, farther from cities and roads and dense populations. And in some ways that can be true. But the ocean is not an empty place in planetary terms. It is connected to coastlines, climates, ecosystems, shipping routes, and the atmosphere above it. So an asteroid striking the sea would still be striking Earth in a very real sense. It would move water, air, and energy on a large scale. It would threaten nearby shores first. And if the event were large enough, it could extend its effects far beyond the point where it first entered the ocean. So whether the asteroid hits land or water, the surface is only the beginning. Because after the blast, after the crater or waves, another stage begins. The sky changes. Dust and debris rise. Sunlight may begin to weaken. And what started as a single impact can begin spreading into a much larger planetary effect. The sky can change after the ground does. That is one of the most important things to understand about a large asteroid impact. The first destruction happens at the surface. The strike, the crater, the blast, the heat, the waves, if it hits the ocean. But after that, the effects do not stay low to the ground. They rise. A large impact can throw enormous amounts of material high into the atmosphere. Dust, pulverized rock, broken minerals, fine particles blasted upward from the crater and the surrounding surface. If the impact is big enough, this material can be carried far above the immediate impact zone and begins spreading across much larger parts of the sky. This matters because sunlight depends on a relatively clear path through the atmosphere. If enough dust and fine debris are lifted high enough, that path begins to change. The sky may become hazy, dimmer, less transparent. Sunlight that would normally reach the surface can be weakened, scattered, or blocked for a time. And dust may not be the only thing in the air. A large impact can also ignite fires across broad areas, especially after a land strike. Burning forests, vegetation, buildings, and other fuel sources can release soot into the atmosphere. That soot can mix with the dust and expand the haze even further. So the darkening is not caused by one thing alone. It can become a combination of rock, ash, soot, and suspended particles all spreading through the air together. This is where the disaster starts becoming more than a local or regional event. Once the atmosphere changes, the consequences can begin reaching far beyond the crater or coastline. Even places untouched by the initial strike may start feeling the aftermath through the sky above them. Sunlight reaching the ground may fall sharply. And sunlight is not just brightness. It is energy. It helps warm the surface. It powers photosynthesis. It helps drive weather and seasonal rhythms. So when sunlight is reduced, the problem quickly extends beyond visibility. The surface may begin cooling. That cooling can affect the air, the land, and the water. Temperatures may drop. Daily heating patterns may weaken. Weather systems may begin shifting in unusual ways. The longer the haze remains, the more those changes can start disturbing ecosystems that depend on stable conditions. This is why the size of the impact matters so much. A smaller event may create a temporary regional haze. A larger event could inject enough material into the atmosphere to produce much broader effects. And at the highest scale, the consequences can become global. That does not mean every impact darkens the whole planet. Most do not. But the larger the impact, the more likely it is that atmospheric effects spread beyond the immediate zone of destruction and begin affecting Earth as a system. This is a different kind of damage than a blast wave or falling debris. It does not arrive in one instant. It builds. The strike happens quickly. The darkening unfolds afterward. People may first notice it as a strange haze, a dimmer sun, a sky that looks wrong for the season or time of day. Then, as days pass, the consequences may begin reaching into temperature, rainfall, growing conditions, and visibility. What makes this especially serious is that the sky connects everything below it. A city can avoid the crater. A distant coastline may escape the first waves. A town far inland may be safe from the blast zone. But once the atmosphere begins carrying dust and soot across large distances, the impact becomes harder to contain. It starts affecting regions that never saw the asteroid itself. That is when the event begins turning from a strike into an environmental crisis. And this is also where the human imagination often shifts. At first, the asteroid is the object of fear, the rock from space, the thing coming down. But after a sufficiently large impact, the greater danger may no longer be the asteroid itself. It may be the altered Earth it leaves behind. A dimmer sky, cooler ground, less sunlight, a planet trying to function under a layer of suspended debris. So the aftermath does not stop with fire or dust rising upward. Those particles begin changing the conditions of life below them, because life on Earth depends on light. And once that light begins to fade, the next part of the story begins. Not in the crater, not in the blast zone, but in fields, forests, oceans, and food webs across the planet. Life depends on steady light and stable cycles. That is easy to forget during normal times. Food can feel constant. Fields grow in season. Oceans keep moving. Stores stay stocked. The world feels organized enough that many people rarely stop to think about how much life depends on sunlight arriving on time, temperatures staying within range, and weather following patterns that living systems can work with. A major asteroid impact could disturb all of that at once. If enough dust, soot, and debris rise into the atmosphere and remain there, sunlight reaching Earth's surface may fall sharply. That immediately matters for plants. On land, plant growth depends on light. Photosynthesis is how plants capture energy and turn it into the food that supports forests, grasslands, crops, and nearly every land food web. If sunlight weakens for long enough, that system begins slowing down. Crops may grow poorly. Some may fail outright. Others may mature too slowly or produce much smaller yields. Fields that depend on a reliable season of warmth and light could suddenly face conditions they were never meant to handle. And sunlight is only one part of it. Agriculture also depends on timing. Temperature, rainfall, soil conditions, the length of the growing season. A major impact could disrupt several of those factors at the same time. If cooling begins, planting and harvest patterns may no longer line up the way they normally do. If rainfall shifts, some places may become drier, while others receive too much at the wrong time. A crop does not need the whole planet to collapse in order to fail. It only needs its conditions to change enough at the wrong moment for the season to be lost. This is why a large impact can create danger far beyond the strike zone. Even places untouched by the crater, fire, or pressure wave may still face food stress later. The problem spreads through systems people depend on every day. And the ocean is not separate from this story. Marine food webs also depend on light, especially near the surface. In the upper layers of the ocean, tiny photosynthetic organisms help form the base of the marine food chain. These organisms may be small, but they support much of the life above them. If sunlight drops enough, surface productivity in the ocean can fall too. That means the consequences may travel upward through marine ecosystems. If the smallest producers struggle, the animals that depend on them struggle next. Then the animals that depend on those animals begin feeling it too. So a darkened sky can affect not only crops on land, but also food chains in the sea. This is what makes reduced sunlight so serious. It reaches into the base layers of life. It does not only threaten one species or one region. It threatens the energy flow that ecosystems rely on. And when energy becomes harder to capture, the entire system begins tightening. Food shortages could then spread in stages. At first, the damage might appear as crop stress, lower harvests, and regional supply problems. Then shortages may widen. Prices may rise. Trade systems may strain. Communities far from the impact may still begin feeling its consequences through disrupted food supply, unstable markets, and growing pressure on what remains available. So the asteroid does not need to strike a farm to affect food. It does not need to hit a fishing ground to affect the sea. It only needs to change the atmosphere enough to interrupt the steady patterns that life depends on. This is one of the quietest but most far-reaching parts of the whole story. A major impact begins as an event in one place, but food systems turn it into something broader. They connect light to crops, crops to people, light to plankton, plankton to marine life, and all of it to the larger structure of survival. That is why the aftermath of a large asteroid impact is not only about explosions, craters, or falling debris. It is also about interruption. The interruption of sunlight, the interruption of seasons, the interruption of growth, and eventually the interruption of food. And once those interruptions begin, the pressure on Earth does not end with a darkened sky. It moves into climate itself. Because a cooler, dimmer planet is not just a short-term inconvenience. It can become a second phase of the disaster, lasting long after the impact flash is gone. A single strike can echo outward into months, years, or even longer of environmental stress. A single impact can echo through the climate system. That is part of what makes a large asteroid impact so different from an ordinary disaster. The first event may happen in a matter of seconds. A flash, a blast, a crater, a darkening sky. But after that, Earth may continue responding for a very long time. If enough dust, soot, and fine debris are lifted high into the atmosphere, sunlight reaching the surface can remain reduced well beyond the day of impact. And if that reduction lasts, cooling begins to spread through the climate system. This is often described as impact winter. The phrase fits because the planet can begin acting as though less solar warmth is reaching it, even if the calendar says otherwise. Days may grow dimmer, temperatures may fall, the usual rhythm of heating and cooling can weaken. Seasonal expectations may stop matching reality. That matters because Earth's climate depends on sunlight as its main energy source. When sunlight is blocked or reduced, the surface does not warm the same way. Land cools. Water surfaces cool more slowly, but they are still affected. air patterns begin shifting. The balance between regions can change. And once that happens, weather may stop behaving in familiar ways. This is where the aftermath of a large impact becomes harder to predict in exact detail, but easier to understand in principle. Less sunlight means less heating. Less heating means climate stress. And that stress can last. Not every impact would produce a long global cooling event. Most would not. But larger impacts could drive enough material high enough into the atmosphere for the effects to continue for months, years, or longer, depending on the scale of the strike and what kind of material was launched into the sky. The longer those particles remain suspended, the longer Earth may struggle under dimmer conditions. Rainfall patterns could shift. Some regions might become drier than usual. Others may see rain arrive at the wrong times or in unusual amounts. Storm tracks could move. Seasonal transitions could become less reliable. Places that depend on a narrow window of warmth and moisture for crops may find that window shrinking or disappearing. And that leads directly to one of the most serious consequences. Growing seasons could shorten or fail. A plant does not care whether sunlight was blocked by clouds, volcanic ash, or impact dust. It only responds to the conditions it receives. If temperatures stay too low, if light remains too weak, or if rainfall patterns shift enough, crops may not develop properly. The result is not just poor growth, but repeated agricultural stress over multiple seasons. This is why climate stress after a major impact can become a second disaster. The first disaster is the strike itself, the immediate destruction, the blast zone, the fires, the waves, the darkening sky. The second disaster is what follows. A cooler planet, failed harvests, disrupted rainfall, pressure on ecosystems and food systems that were already weakened by the initial event. And because climate connects so many parts of Earth at once, this second phase may reach places very far from the impact site. A country untouched by the crater could still suffer crop loss. A coastline far from the strike could still feel shifts in weather and food supply. An ecosystem nowhere near the original event could still decline because the conditions it depends on no longer hold steady. That is the wider meaning of impact winter. It is not just colder weather. It is a loss of normal climate function. The planet keeps moving. The sun is still there. Day still follows night. But the systems that distribute light, warmth, and moisture begin operating under stress. This is also what makes large impacts so historically important. They do not need to destroy every place directly in order to change life on Earth. They only need to change the climate deeply enough that life can no longer keep pace with the new conditions. And Earth has likely experienced exactly that before. Long before humans existed, one impact appears to have changed the course of life on this planet in a way that can still be seen in the fossil record today. It happened about 66 million years ago. It struck near what is now the Yucatan Peninsula, and it is remembered not only because of the crater it left behind, but because of what followed afterward. Darkness, cooling, ecological collapse. In other words, the clearest ancient example of how one asteroid can reshape an entire world. Earth has been hit before. That is one of the reasons asteroid impacts hold such power in the human imagination. They are not only theoretical, they are part of Earth's history. And the most famous example happened about 66 million years ago. near what is now the Yucatan Peninsula in present-day Mexico, a large asteroid impacted Earth and left behind what we now call the Chicxulub crater. Today, much of that crater is buried and difficult to see in the simple way people imagine a crater. But its presence has been studied in detail. It remains one of the clearest pieces of evidence that a single cosmic event can alter life across an entire planet. This impact matters not just because it happened, but because of what followed. It is strongly linked to the mass extinction event that ended the age of non-avian dinosaurs. That does not mean every dinosaur vanished in the exact moment of impact. The deeper story is larger than that. The impact appears to have triggered a chain of environmental changes so severe that many forms of life could no longer survive the conditions that followed. In other words, the asteroid did not simply create a crater. It changed Earth's systems. The immediate effects near the impact site would have been immense. The energy released at impact would have been far beyond anything in ordinary human experience. Rock was crushed, heated, and thrown outward. Material was blasted high into the atmosphere. The surrounding region would have faced catastrophic damage in the opening phase alone. But as this video has been building toward, the most far-reaching consequences of a very large asteroid impact do not end at the crater. They spread into the sky. Dust and pulverized rock likely rose high into the atmosphere. Fires may have spread over large areas, adding soot to the air. Sunlight reaching the surface appears to have dropped sharply afterward. And once that happened, Earth's climate and food systems would have come under severe pressure. This is what makes the Chicxulub impact such an important example. It helps show that a sufficiently large asteroid does not need to destroy every ecosystem directly. It only needs to alter the conditions of life deeply enough that ecosystems begin collapsing on their own. Plants would have struggled under dimmer skies. Food webs on land would have been disrupted. Marine systems may also have suffered if sunlight reaching the upper ocean fell enough to reduce surface productivity. Cooling likely followed. Growing conditions changed, and species already adapted to one version of Earth suddenly faced another. The result was ecological collapse on a massive scale. Many species disappeared. Among the most famous were the non-avian dinosaurs, which had dominated Earth for a very long time before this event. Their loss is why the Chicxulub impact is so often remembered as the asteroid that ended the age of dinosaurs. But it also did something else. It changed the future. When so many species vanish, ecosystems do not stay frozen. New opportunities open. Other lineages survive and expand. The world after the impact was not simply emptier. It was different. The history of life continued, but on a changed planet, under changed conditions, with changed possibilities. That is why this ancient event still matters to us now. It is the clearest known example of how one asteroid impact can reshape life on Earth at the largest scale. Not just locally, not just regionally, but globally. It reminds us that impact danger is real, even if such events are rare on human timescales. It reminds us that the solar system has touched Earth before, in ways powerful enough to alter biological history. And it gives weight to the question running through this whole video. What would really happen if an asteroid hit Earth? The answer is not only found in physics models or modern observations. Part of it is already written into the planet's past. A buried crater, a break in the fossil record, a lost age of giant animals, and the long ecological aftermath that followed one of the most consequential impacts Earth has ever known. Still, that event was ancient. It belongs to deep time, long before people, cities, agriculture, or satellites. So after looking back 66 million years, the next question becomes more immediate. How often do impacts like this actually happen? Because the sky carries risk, but not every risk is equally likely. The sky carries risk, though the biggest disasters are rare. That is an important balance to hold. After learning what a large asteroid impact could do, it is easy for the mind to drift toward the most dramatic possibilities. A crater, a darkened sky, global climate stress, mass extinction. The scale of it can make the danger feel immediate, as though Earth is constantly on the edge of another Chicxulub-sized event. But that is not how the sky usually behaves. Earth is struck by material from space all the time, though most of it is tiny. Small meteoroids enter the atmosphere constantly. Many are no larger than grains of dust or small pebbles. They burn up high above the planet and never become a true danger on the ground. What people sometimes see as brief streaks of light in the night sky are often examples of this normal process. In that sense, Earth is always interacting with space. But there is a huge difference between constant small arrivals and rare major impacts. As object size increases, serious events become much less common. A small object that creates a visible meteor is ordinary. A larger object that produces an airburst over a populated area is much less common. A still larger impact capable of damaging a city or region is rarer again. And a civilization-altering or extinction-level event sits at the far end of the scale, where events are extremely rare on human timescales. That phrase matters. Human timescales are short. A human lifetime feels long to us. Recorded history feels vast. Even a few thousand years can seem distant and almost unimaginable from an everyday perspective. But Earth's history is measured in millions and billions of years. On that scale, rare does not mean impossible. It means uncommon enough that many generations may pass without ever witnessing such an event. This is one reason asteroid risk can feel hard to place emotionally. The danger is real. The consequences can be enormous. But the largest impacts do not belong to the rhythm of ordinary life. They are not like storms that return every season or earthquakes that occur regularly in known zones. The biggest impacts are low-frequency events. And yet low frequency does not mean unimportant. Some dangers deserve attention, not because they happen often, but because the consequences are so large when they do happen. That is the category asteroid impacts belong to. A house fire is far more likely to affect one person directly than a giant asteroid impact. But a giant asteroid, if one were truly on course, could affect whole regions, nations, or more. So rarity and seriousness have to be held together in the same thought. This is also why scientists divide asteroid threats by size and consequence, rather than talking about all space rocks as though they carry the same level of danger. Most do not. Most never reach the ground. Most are not large enough to matter beyond a streak of light. Many of the objects that could cause real damage are still relatively small compared with the planet itself. And the truly enormous ones, the kind linked to global catastrophe, are the rarest of all. That should not lead to complacency, but it should create perspective. The asteroid story is not that Earth is constantly one step away from destruction. It is that Earth moves through a solar system where impacts are part of reality, though the most serious ones are uncommon enough that careful watching matters more than panic. That distinction is important, because once we understand that major impacts are rare, another question naturally follows. If they are rare, why track them so carefully? The answer is simple. Because warning changes everything. For the smallest objects, there may be little reason for concern. For mid-sized threats, time could allow evacuation or emergency planning. For larger threats, time could mean the difference between helplessness and a possible deflection attempt. That is why space agencies and astronomers spend so much effort watching the sky. Not because giant impacts are likely tomorrow, but because even rare dangers deserve attention when the stakes are high enough. In other words, rarity does not remove responsibility, it clarifies it. The modern response to asteroid risk is not fear, it is observation. Careful measurements, repeated surveys, orbital calculations, a quiet effort to notice what is out there before it ever becomes a problem. And that leads directly into the next part of the story. How scientists actually search for dangerous asteroids. Because protecting Earth from a rare danger begins with one simple task: finding the object first. Watching the sky is a quiet form of protection. That may be one of the most reassuring parts of this whole story. Asteroids are not only something humanity fears from a distance. They are also something humanity studies, tracks, and watches with increasing care. The first step in dealing with a dangerous asteroid is simple in principle, though difficult in practice. You have to find it. That sounds straightforward until you picture what astronomers are really trying to do. They are searching for dark objects in a vast sky, often small, often faint, and often moving slowly enough at first that they can be hard to notice against the background of stars. So the work begins with telescopes. Astronomers use ground-based and space-based observing systems to scan the sky for near-Earth objects, often called NEOs. These are asteroids and comets whose orbits bring them relatively close to Earth's orbit. Not all near-Earth objects are dangerous, but they are the group that deserves careful attention because their paths can bring them into Earth's neighborhood. Many survey programs do not just look at the sky once. They scan the same regions repeatedly. That repetition matters because movement is one of the main clues. A star stays fixed in the same pattern relative to other stars over a short period of time. An asteroid does not. If astronomers take images of the same patch of sky and compare them, a moving object may reveal itself as a small point, shifting from one position to another. That is how many detections begin. Not as dramatic discoveries, but as tiny changes between images. Once an object is found, the next task is measurement. Astronomers record its position in the sky very carefully. They measure its brightness. They observe how it moves over time. From those observations, they begin calculating its orbit. The orbit is the heart of the matter. An asteroid is not dangerous simply because it exists. It becomes important because of the path it follows around the Sun. So scientists use repeated observations to estimate where the object is going, where it has been, and whether its future path may ever come close to Earth. At first, those calculations may be uncertain. A newly discovered asteroid might only have been observed for a short time. Its orbit may be only roughly known. That is why follow-up observations are so important. The more times astronomers see the object, and the longer they track it, the better they can refine the orbit and reduce uncertainty. In other words, the early picture may be blurry, but with time and more data, it becomes sharper. Computers play a major role here. Modern asteroid tracking is not just people looking through telescopes. It is also a problem of data, motion, and prediction. Computers help compare images, detect moving objects, link new sightings to known asteroids, and calculate possible future paths. They can project an orbit forward to see whether an object might intersect Earth's orbit later on. That does not mean every close approach is dangerous. In fact, most are not. Many objects pass by at safe distances. Some may sound close in astronomical terms while still being far beyond any actual impact risk. This is another reason precise tracking matters so much. It helps separate the interesting from the threatening. Brightness also matters, though in a limited way. A brighter object may be easier to detect, but brightness alone does not reveal everything. An asteroid might look dim because it is small, or because it is dark, or because it is far away. So astronomers combine brightness with other information to estimate size and understand what kind of object they may be tracking. And all of this effort serves one central purpose: time. The more time humanity has, the more choices humanity has. If a dangerous asteroid were discovered only days before an impact, there may be little anyone could do beyond warning the region at risk. But if it were found years or decades in advance, the situation changes completely. Scientists could track it more accurately. Governments could plan. And in some cases, a deflection attempt might even become possible. That is why asteroid surveys matter so much. They are not only cataloging rocks in space, they are buying time in advance. They are turning surprise into awareness. And awareness is the first real form of defense. So when people imagine asteroid protection, they may picture spacecraft, technology, or some dramatic last-minute rescue. But the real beginning is quieter than that. A telescope scanning the sky, a faint point of light moving between stars, a series of measurements, an orbit traced across time. Because before humanity can stop a threat or prepare for one, it has to do something much simpler. It has to notice that the object is there. And once it does, the next question becomes the one people almost always ask next. Could we actually stop one? Prevention depends on time. That is the most important truth in this part of the story. When people imagine stopping an asteroid, they often picture something dramatic. A last-minute mission, a direct hit, a desperate attempt to save Earth just before impact. But in reality, planetary defense works best when nothing dramatic is needed at all. Because if a dangerous asteroid were discovered early enough, humanity might not need to destroy it. It may only need to nudge it. That is a very different idea. The goal would not necessarily be to blow the asteroid apart or erase it from space. In many cases, the better strategy would be to change its path by a very small amount long before it ever reaches Earth. And that small change matters because orbits unfold over time. If you shift an asteroid's position just a little years in advance, that tiny adjustment can grow into a huge miss later. What would have been a direct impact could become a harmless pass at a safe distance. This is one of the strangest and most hopeful parts of asteroid defense. The earlier you act, the less force you may need. That is because the asteroid is not being stopped in the ordinary sense. it is being redirected. A slight orbital change, if made early enough, may be all it takes to keep Earth and the asteroid from arriving at the same point in space at the same time. There are several ideas for how that might be done. One of the most direct is called a kinetic impactor. This means sending a spacecraft to collide with the asteroid at high speed in order to change its motion slightly. The spacecraft does not need to destroy the asteroid. It only needs to transfer enough momentum to alter the orbit by a small amount. Again, the key is time. A tiny change now can become a large separation later. Another idea is the gravity tractor. This sounds almost gentle compared with what people usually imagine. In this concept, a spacecraft would fly near the asteroid for a long period of time, using its own small gravitational pull to slowly tug the asteroid onto a slightly different path. The force would be tiny, but over enough time, even a tiny force can matter. There are other proposed methods too. Some involve changing the surface in ways that alter how it absorbs and re-radiates sunlight, which can slowly affect motion. Some involve more forceful intervention, but all of them return to the same central idea. Find the object early, act early, change the orbit before impact becomes unavoidable. This is why time matters more than drama. A last-minute response would be far harder. If the asteroid were discovered only shortly before arrival, there may not be enough time to launch a mission, reach it, and meaningfully alter its orbit. That is why the search work discussed in the last section is so essential. Deflection begins with detection, and humanity has already tested part of this idea in practice. In 2022, NASA's DART mission intentionally impacted a small asteroid moonlet named Dimorphos. The goal was not to save Earth from an immediate threat, but to test whether a spacecraft could change an asteroid's motion. And it did. The impact measurably changed Dimorphos's orbit around its larger companion asteroid. That result mattered. It showed that asteroid deflection is possible in principle, not as science fiction, not only as theory, but as something real enough to be tested and measured. That does not mean every future asteroid problem is solved. Different asteroids are different sizes, different shapes, different compositions. Some may be loose rubble piles. Some may be denser and more solid. A successful test on one object does not guarantee an easy answer for every future threat. But it proved that changing an asteroid's motion is not just an idea. It can be done. And still, the real challenge remains the same. Finding dangerous objects early enough to act. That is the heart of planetary defense. Not a heroic final moment, but early awareness. The sooner the object is found, the more realistic prevention becomes. The later it is found, the fewer choices remain. So when people ask whether humanity could stop an asteroid, the most honest answer is this. Sometimes, perhaps yes, but only if we know about it early enough. Because survival may depend less on force than on foresight. And if prevention is not possible, then warning becomes the next best form of protection. Which raises another important question. What could warning actually do? Time can reduce harm. That is the value of warning. It cannot make a dangerous asteroid harmless by itself. It cannot remove the object from the sky. It cannot undo the physics of an impact. But it can change what people do before the event happens, and that can matter enormously. The effect of warning depends on the size of the object and the kind of event expected. For smaller impacts, warning could allow emergency planning and evacuation. If scientists knew an object was likely to explode in the atmosphere over a certain region, officials might be able to alert the public in advance. People could be told to stay away from windows. Emergency services could prepare for injuries, broken glass, and damaged buildings. Air traffic might be redirected. Sensitive infrastructure could be protected where possible. That kind of warning would not erase the event, but it could reduce casualties. The same is true for a smaller ground impact. If the likely impact zone were known early enough, people might be evacuated from the area. Roads could be cleared. Hospitals could prepare. Power systems, communications networks, and emergency response teams could be positioned with the event in mind. Even if the physical damage remained severe, the number of people caught directly inside it could be much lower. For ocean impacts, warning could matter in a different way. Nearby coastlines might have time to prepare for incoming waves. That could mean evacuation from low-lying areas, movement of ships, closure of ports, and emergency coordination for coastal communities. Again, the warning would not stop the water from moving, but it could keep more people out of its path. Airbursts are another important case. As the Chelyabinsk event helped show, one of the biggest dangers from an atmospheric explosion can come from the way people react in the first moments. A bright flash draws attention. People move toward windows to look. Then the shockwave arrives and glass shatters inward. With warning, even simple protective instructions could save lives. Stay indoors. Move away from windows. Do not go outside to watch. Sometimes survival depends on surprisingly basic actions taken early enough. But warning has limits. For truly enormous objects, warning would not turn the event into something manageable in the ordinary sense. A very large impact could exceed the ability of any one city, region, or even nation to fully prepare for it. Evacuation might help in some areas. Coordination would still matter. Governments could protect archives, move resources, organize shelters, and prepare emergency food and medical responses. But warning would not make the danger small. This is the difficult truth at the center of the section. Knowledge does not erase danger. It changes outcomes, but only within the scale allowed by the event itself. That distinction is important. Warning is not the same as prevention. Prevention aims to stop the impact from happening at all. Warning accepts that the impact may happen and tries to reduce the damage to human life and society as much as possible. So the value of warning depends on context. For a modest event, warning might save many lives. For a regional disaster, warning could shape evacuation and response. For a larger event, warning might become more about coordination, continuity, and survival planning than direct protection from the impact itself. Even then, it still matters. Because when danger cannot be removed, understanding becomes its own form of strength. It allows people to act with purpose instead of confusion. It gives governments time to organize rather than improvise. It turns complete surprise into at least some degree of preparation. And that changes the human meaning of the event. An unexpected asteroid impact feels like pure helplessness. A predicted one, even if still frightening, becomes something people can face with information, decisions, and response. That may be one reason asteroid impacts stay with us so strongly in the imagination. They sit at the edge between knowledge and helplessness, between ordinary life and planetary forces, between what humans can prepare for and what remains larger than us. So warning matters greatly, but it also reminds us of something deeper. Some dangers feel so large not only because of what they can do, but because of what they reveal. They reveal that Earth is not sealed off from space. They reveal that ordinary life exists beneath a moving sky. And they reveal how thin the line can sometimes be between a normal day and a planetary event. Some dangers feel larger than daily life. Asteroid impacts belong to that category. There are many dangers on Earth that people understand through experience. Storms, floods, fire, drought. Even when those events are frightening, they still feel like part of the world we already know. They belong to weather, land, water, and the systems of Earth. Asteroid impacts feel different. They come from outside. That alone gives them a special place in the human mind. An asteroid is not just a disaster. It is a disaster that arrives from space. It crosses the boundary between the familiar world below our feet and the much larger universe beyond it. And that makes the idea hard to forget. Asteroid impacts combine space, chance, and fragility in a single image. A rock drifting through darkness. A planet full of life moving along its own path. And the possibility that, at some moment, those paths could meet. That image stays with people because it feels both simple and enormous at the same time. It is simple because the basic idea is easy to grasp. Something from the sky hits Earth. But it is enormous because of what that idea contains. Astronomy, deep time, extinction, human vulnerability, the scale of the solar system, the fact that our world is not standing still, but traveling through a region of space filled with objects that have their own long histories and their own motions. In that sense, asteroid impacts remind us that Earth is part of a wider cosmic environment. That may be one of the deepest reasons they remain so powerful in thought and storytelling. They break the illusion that Earth is separate from the rest of the universe. They remind us that the sky is not just a backdrop. It is a place, a real environment, a moving one, a place with debris, orbits, gravity, and ancient objects still circling the sun long after the planets formed. And that makes ordinary life feel thinner in a strange way. A person can be walking home, making dinner, driving to work, looking up at a quiet sky. And above all of that, the solar system is still in motion. That is part of what asteroid impacts reveal so clearly, how thin the line can be between ordinary days and planetary events. Most days, nothing happens. The sky stays calm. Earth continues on. But the fact that a major change could begin with one object crossing one path gives the subject a lasting emotional weight. It feels ancient and possible at the same time. Ancient because we know impacts shaped the history of planets long before human beings existed. The Moon carries craters, Mercury carries them, Mars carries them, Earth carries them too, though weather, oceans, and geology have hidden many of its older scars. Possible because impacts are not only part of the past, they remain part of the solar system now. Rare at the larger scale, yes, but still real. That combination is powerful. Something ancient, something rare, something still possible. It lingers in the mind because it connects personal vulnerability with astronomical scale. A person is small, a city is small, even a civilization is small compared with planetary history. Asteroid impacts force that perspective into view. They remind us that human life unfolds inside a much larger setting. A setting shaped not only by biology and weather and geography, but by celestial motion. And yet this does not have to lead only to fear. There is another side to it. The same subject that humbles us also teaches us. It shows us that human beings can look outward, study danger, understand orbits, read the scars of ancient impacts, and even begin testing ways to prevent future ones. So asteroid impacts do not only reveal fragility, they also reveal awareness. We are vulnerable, yes, but we are not blind. That may be the most balanced way to hold this idea. Asteroid impacts stay in human imagination because they are one of the clearest symbols of what it means to live on a small inhabited world beneath a vast and active sky. They remind us that Earth is precious, that normal life rests inside larger motions, and that understanding those motions is part of what gives us perspective. So the subject begins in fear for many people. A rock from space, a threat from above. But if we stay with it long enough, it leads somewhere quieter, toward scale, toward humility, toward the strange comfort of seeing Earth more clearly for what it is, a sheltered world, but never an isolated one. Our planet is sheltered, though never isolated. That may be one of the most calming truths to end on. Earth is not defenseless. It is not simply exposed beneath an open sky with nothing standing between life and the rest of space. In many ways, this planet is protected. Its atmosphere is one of those protections. Every day, Earth's atmosphere destroys countless tiny objects before they can ever reach the ground. Dust-sized particles, grains, pebbles, and small fragments enter from space constantly. Most burn up high above us. They become faint streaks of light, brief flashes, or events so small that no one notices them at all. Without the atmosphere, Earth's surface would be struck far more often. So when we look up at the sky and feel that it is empty, part of what we are really feeling is the success of a shield we do not usually think about. A deep layer of air quietly protecting the surface below. And Earth is not the only place in the solar system that tells this story. The Moon tells it too. So do Mercury and Mars. These worlds preserve impact scars much more clearly than Earth does. They do not have the same weather, flowing water, thick atmosphere, or active geology that help erase older marks here. So their surfaces still carry visible reminders of what the solar system has always been like. They are records of a busier sky. Craters across the Moon remind us that impact is not some strange exception in planetary history. It is part of how worlds are shaped. Planets and moons do not form and then remain untouched forever. They exist inside a system full of motion, gravity, debris, and time. Earth has its own scars too, though many are hidden. Some have been worn down by wind and rain. Some lie beneath forests or oceans. Some have been altered by tectonic activity and the slow reshaping of the surface. Earth looks softer than the Moon, in part because it is more active, more weathered, and more alive. But that does not mean it has escaped the history written elsewhere. It means the record here is harder to read. And this is where planetary science becomes so valuable. The more humanity has studied craters, asteroids, orbits, and the history of impacts, the more clearly this risk has come into view. What once may have felt like myth or cosmic mystery can now be understood with far more precision. We can estimate asteroid sizes, track their motion, study ancient craters, model impacts, test deflection methods. We understand this danger more than any generation before us. That does not make the sky simple, but it does make it less mysterious in one important sense. We no longer have to face it blindly, and that is worth holding on to, because the solar system is active, not chaotic in the sense of random madness, but active in the sense of ongoing motion. Planets orbit, moons orbit, asteroids orbit, dust drifts, comets return. Gravity shapes paths across millions and billions of years. Nothing is truly standing still. To live on Earth is to travel through that motion every day. Even now, while sitting still in a chair, standing at a window, or lying awake at night, you are moving with Earth. The planet is rotating. It is orbiting the Sun. The solar system itself is moving through the galaxy. And all the while, the sky above remains part of that greater system, not separate from it. That can sound unsettling at first, but it can also be strangely grounding, because it reminds us what Earth really is. Not the center of everything, not cut off from the rest of the universe, but a small living world traveling through a larger cosmic setting, protected in many ways, vulnerable in some, and understandable more and more with time. That is the balance. Earth is sheltered. Its atmosphere protects it. Its scientists watch the sky. Its history has been studied. Its risks are real, but not unknowable. And yet Earth is never isolated. It remains part of a solar system that still carries the marks of its own formation. A solar system where ancient rocks still move between worlds. A solar system where the sky is not a ceiling, but a place. So in the end, asteroid impacts lead us back to a bigger perspective. Not just fear of what could happen, but understanding of where we are. We live on a world beneath a moving sky, protected though not sealed away, small though not insignificant, and always part of something much larger than daily life allows us to feel. Which is perhaps the calmest place this question can leave us, not in panic, but in perspective. So in the end, an asteroid impact can mean many different things. It can be a brief streak of light that burns away harmlessly overhead. It can be an airburst that never reaches the ground, yet still causes damage below. It can be a crater-forming impact with severe local consequences. Or, at the larger scale, it can become a planetary turning point that changes climate, food systems, and the course of life itself. That is part of what makes this question so powerful. What would really happen if an asteroid hit Earth? The answer depends on size, on speed, on angle, on composition, on whether the impact happens over land or ocean, and on how much warning humanity has before the event unfolds. Those details matter because asteroid impacts do not come in one standard form. They exist on a scale, from small atmospheric flashes to world-changing events. And Earth has lived through that scale before. Across deep time, this planet has been touched by impacts of many kinds. Some left only temporary traces. Some left craters. Some helped reshape the history of life. The sky above us may feel calm, but Earth's past reminds us that calm and motion have always existed together. Still, there is something reassuring in what we know now. Humanity understands this danger more clearly than ever before. We can track near-Earth objects. We can study ancient craters. We can model how impacts unfold. We have even tested the first real steps toward asteroid deflection. That does not make Earth invulnerable. But it does mean the sky is not as mysterious as it once was. And maybe that is the most peaceful place to leave this question. Not with panic, not with the feeling that danger is always just above us, but with perspective. Earth is a small world, yes, but it is also a watched world, a studied world, a world protected by its atmosphere, guided by knowledge, and carried through space by the same cosmic motions that shaped everything around it. So when we look up at the night sky, we are not looking at emptiness. We are looking at a living planet moving through an ancient and active solar system. A place of beauty, a place of history, a place where even rare dangers can teach us something deeper about scale, fragility, and the strange privilege of being here at all. And in that sense, the question was never only about destruction. It was also about perspective, about what Earth is, about where we are, and about what it means to live beneath a sky that looks still, even while everything is moving.